In 1948, every mathematical calculation of an electron's energy resulted in an impossible 100% failure rate. Experiments at Columbia University revealed a 100% discrepancy when comparing theoretical models to the actual. However, your entire physical body depends on the precise subatomic stability these led. At the 1948 Pocono Manor conference, young Richard Feynman stood before a mocking J. Robert Oppenheimer to present a new visual language. While the giants of physics saw only meaningless scribbles, Feynman was actually sketching the blueprints for our modern understanding of quantum reality. Now you have to imagine the scene to really feel the tension. It's June 1948, at a secluded resort in the Pocono Mountains of Pennsylvania. The air is thick with the scent of pine, expensive tobacco, and the collective anxiety of the 28 smartest men on the planet. You have Niels Bohr there, the grandfather of the atom, Robert Oppenheimer, fresh off the Manhattan Project, Edward Teller, and Hans Bethe. These were the gods of the new atomic age, but they were gods in crisis. For nearly 2 decades, their crown jewel, Quantum Electrodynamics, or QED, had been broken. Every time they tried to calculate something as simple as the energy level of an electron, the math didn't just fail, it exploded. It gave them an answer of infinity. In physics, an infinite answer is nature's way of laughing at your ignorance. It means your theory is missing something fundamental about the way the world is put together. The day before Feynman took the floor, a young Julian Schwinger had given an 8-hour lecture. It was a tour de force of classical high-level mathematics, hundreds of lines of intricate, dense formalisms that seemed to tame the infinities. The elite were impressed. This was the physics they understood. Then came Feynman. He didn't have pages of formal derivations. He took a piece of chalk and started drawing what we now call Feynman diagrams, those little squiggles that represent particles dancing through space-time. To Feynman, an electron moving through time was just a line, and a photon was a wavy trail. He was trying to show them that you could bypass the nightmare of the math by simply visualizing every possible path a particle could take. But to Bohr and Oppenheimer, it looked like he was cheating. He was playing with pictures while they were trying to solve the secret. Bohr actually stood up, walked to the blackboard, and lectured Feynman for several minutes on the uncertainty principle, convinced that these diagrams violated the most basic tenets of quantum mechanics. He thought Feynman was trying to track the path of a particle, which was supposed to be impossible. Feynman tried to explain that it wasn't a literal path, but a mathematical shorthand for a sum over histories. But the graybeards weren't listening. He sat down, defeated, feeling that he had failed to communicate a truth he could see as clearly as his own hand. He was the man who saw the universe in pictures, standing in a room full of men who could only see it in numbers. The Pocono showdown was, on the surface, a total disaster for Feynman. But as we now know, those squiggles weren't just a shorthand. They were a map to a new dimension of understanding that would eventually earn him the Nobel Prize in 1965 and change the way we look at reality forever. Nature was screaming, reality was collapsing into a black hole of impossible mathematics. Richard Feynman just wanted to draw a few little pictures. In the shadow of the late 1940s, the greatest minds in physics returned from the Manhattan Project to find their intellectual house on fire. Quantum Electrodynamics, or QED, was supposed to be the ultimate description of light and matter, but it was producing answers that defied all common sense. By 1947, theoretical physics was in a state of terminal crisis. The problem was something called the self-energy of the electron. See, according to the equations handed down by the great Paul Dirac at Cambridge, an electron isn't just a tiny ball. It's a point that creates an electric field around itself. But that field has energy, And because Einstein showed us that energy and mass are two sides of the same coin, that field energy adds to the electron's mass. The closer you get to the electron, the stronger the field. And since a point has zero radius, the math tells you the energy becomes infinite. This wasn't just a small error. It was like trying to calculate the weight of a pebble and having your scale tell you it weighs more than the entire galaxy. Richard Feynman, a brilliant young Jewish American from far Rockaway, Queens, was sitting in his office at Cornell University feeling the weight of this failure. He had a thick New York accent and a personality that was more jazz musician than ivory tower academic. He hated the formal, stilted way physics was being taught. To him, if you couldn't visualize what was happening, you didn't really understand it. He looked at the legacy of the 1930s, the work of Oppenheimer at Berkeley and Heisenberg in Germany, and saw a mess of mathematical squiggles designed to hide the fact that the theory was broken. While Feynman was at Cornell, another young genius was attacking the same problem from the opposite direction. Julian Schwinger was the quintessential Manhattan intellectual. He was dapper, often seen in well-tailored suits and driving a sleek Cadillac, possessing a formal elegance that made him the Mozart of physics. If Feynman was the earthy, intuitive rebel, Schwinger was the high priest of formalism. At Harvard, Schwinger was developing a massive, complex mathematical architecture to solve the infinity problem. He was working on something called renormalization. Think of renormalization like this. Imagine you are trying to measure the price of a suit, but the price tag says infinity. However, you notice that the tax on the suit is also infinity. Schwinger's radical idea was that if you subtract the infinite tax from the infinite price in just the right way, you might be left with a finite, real-world cost of $300. It was a mathematical shell game of the highest order. He was trying to redefine the bare mass and charge of the electron, values we can never actually see, to cancel out the infinities of the quantum vacuum. What started as a math problem was about to become a war for the soul of physics. The vacuum, you see, isn't empty. Leonard Susskind often in the quantum world, particles are constantly popping in and out of existence, virtual photons and electrons that live on borrowed time. When a real electron moves through space, it's constantly interacting with this ghost crowd. This is the heart of the infinity crisis. Every time an electron emits a photon, that photon can turn into an electron-positron pair, which then annihilates back into a photon, which then gets absorbed by the original electron. There are an infinite number of these loops, and each loop adds another infinity to the calculation. Schwinger was handling these loops with pages and pages of density. He was a master of the Green's function and operator theory. His lectures at the radiation lab during the war had already become legendary for their rigor. But Feynman was getting frustrated. He didn't want to subtract infinities. He wanted to understand the process. He started thinking about his path integral formulation. The idea that a particle doesn't just take one path from point A to point B, but every possible path simultaneously. Feynman would sit in his cramped Cornell office or sometimes in a local strip club where he liked to work, scribbling what looked like children's doodles. He was trying to map out these infinite interactions of the vacuum using a visual shorthand. He was looking for a way to turn the mathematical disaster into a story. He imagined an electron going forward in time, then suddenly turning into a positron and go to the rest of the world. These were just squiggles. But to Feynman, they were a map of a deeper reality that Schwinger's equations were hiding. The pressure was mounting. Hans Bethe, Feynman's mentor and the man who figured out how the sun shines, was pushing Richard to finish his work before the big meeting at Pocono Manor. The infinity crisis wasn't just a headache for theorists, it was blocking progress in understanding the Lamb shift and the magnetic moment of the electron. Physical measurements that were coming in from Columbia University, the stakes were absolute. If they couldn't fix QED, the entire project of 20th century physics, the dream of a unified understanding of the universe, would remain a shattered mess of It was 1948, and the showdown between the formalist and the jokester was about to redefine what we call knowledge. To understand what Feynman was doing, you have to realize that he wasn't thinking in the language of formal mathematics. He wasn't starting with the heavy Greek-laden operators that Paul Dirac or Werner Heisenberg used. No, Feynman was looking at the world like a child who hadn't been told what was impossible yet. He looked at a single electron moving from point A to point B and asked a question that sounded like a joke. In the classical world, the world of billiard balls and planets, things take the most efficient route. If you throw a ball to a friend, it follows a nice, predictable parabola. It doesn't detour through the moon or do a loop-de-loop around your head before landing. But Feynman suggested that in the quantum world, the rules of common sense are a polite fiction. He proposed that an electron doesn't just travel along a single line. Instead, it takes every single possible path from A to B simultaneously. It sounds like a hallucination. In Feynman's sum over histories, that electron is going in a straight line, sure, but it is also going to the corner store. It is going to the edge of the galaxy and back. It is zipping backward in time and spinning through the center of a star. It is exploring every nook and cranny of the universe on its way to the destination. Now you might ask, if everything is taking every path, why don't we see? This is where the brilliance of Feynman's intuition kicks in. He used a concept called the phase. Imagine that for every path the particle takes, it carries a little stopwatch. As the particle moves, the hand on that watch spins around and around. When the particle finally arrives at point B, we look at where that hand is pointing. For the paths that are wild and crazy, the ones that zigzag across the cosmos, those little stopwatch hands end up pointing in every which way. When you add them all up, they cancel each other out. One points up, another points down, and the result is zero. But for the paths that are very close to what we call the classical path, the path that a normal ball would take, those stopwatch hands all end up pointing in roughly the same direction. They reinforce each other, they sing in harmony. This was his path integral formulation. It was a visual, intuitive way of showing that the solid reality we see is just the place where all the quantum madness happens to add up instead of cancel out. Everything they believed up to this point was wrong. But the most shocking, Feynman didn't just have an analogy, he had a way to draw it. He realized that if he could represent these complex mathematical interactions with simple little lines and squiggles, he could bypass the infinite equations that were breaking everyone else's brains. He started drawing elective interactions as if they were sticks and loops. A straight line for an electron here, a wavy line for a photon there. To the old guard at Pocono Manor, like Niels Bohr, this looked like a child's doodles. They wanted to see the rigorous Bohr actually stood up and lectured Feynman, telling him he didn't understand the basics of uncertainty. But Feynman wasn't confused. He had found a way to see through the fog of infinity by treating the universe as a sum of all its many stories. He was saying that reality isn't a single track. It is a grand, shimmering chorus of possibilities, and his squiggles were the musical notation for the entire symphony. He was essentially telling the greatest physicists on Earth that they were so busy looking at the trees, they had forgotten that the forest was made of ghosts. So, imagine the scene after the Pocono disaster. Feynman is frustrated, sitting in his office at Cornell, wondering why the greatest minds in the world couldn't see what was as plain as day to him. Meanwhile, Julian Schwinger is at Harvard, being hailed as the new savior of physics because his math, though it looked like a dense, impenetrable forest of thorns, actually worked. You had two men standing on opposite sides of a canyon, both looking at the same mountain of quantum reality, but describing it in languages that didn't even share an alphabet. This is where a young, skinny Englishman named Freeman Dyson enters the story. Dyson was only 24, a mathematical prodigy who had just arrived at Cornell to study under Hans Bethe. He was quiet, observant, and possessed a rare kind of intellectual bifocals. He could sit in a room with Feynman and watch him scribble those funny little pictures on a napkin, seeing the raw physical intuition of a man who thought like a particle. Then he could turn around and spend weeks agonizing over Schwinger's formalist, hyper-elegant equations that treated the electron like a smooth, continuous wave in a field. Now, you have to understand the magnitude of the problem here. In the late 1940s, physics was essentially broken. If you tried to calculate the energy of an electron, the math gave you infinity. If you tried to calculate its charge, you got infinity. It was like trying to use a scale to weigh a bowling ball and having the needle spin around until the machine exploded. Schwinger's method was a surgical way of renormalizing those infinities, basically a way of hiding the mess under a very expensive rug. Feynman's method, the path integral, was more like a wild, chaotic map of every possible way a particle could move. To everyone else, they were different theories, but Dyson had a hunch. He realized that Feynman wasn't just doodling. He had discovered a secret shorthand for the most complex but the most shocking. In the summer of 1948, Dyson took a cross-country Greyhound bus trip from California back to the East Coast. For 48 hours, he sat in the back of that bus, staring out at the rolling hills of Nebraska and the vast. He didn't have a notebook with him. He didn't have a blackboard. He just had the silence of the road and those two conflicting versions of. And then, somewhere in the middle of the night, it clicked. He saw it. He realized that Feynman's squiggles were not just helpful illustrations. They were the exact mathematical equivalent of Schwinger's formal operators. If Schwinger's math was a massive 500-page instruction manual for building a clock, Feynman's diagrams were a single, perfect photograph of the clock's gears. They told the same story about how light and matter interact, but Feynman's way was 1,000 times more efficient. When Dyson finally stepped off that bus and reached the Institute for Advanced Study in Princeton, he knew he had the key to the kingdom. He sat down and wrote a paper titled The Radiation Theories of Tominaga, Schwinger, and Feynman, which remains one of the most important documents in the history of science. He proved that the intuitive visual world of Feynman was the same as the rigorous formal world of Schwinger. He bridged the gap. More importantly, he gave the Feynman rules to the world. He showed other physicists that they didn't need to be geniuses like Julian Schwinger to solve these problems. They just needed to learn how to draw the diagrams. He took the fire of the gods and brought it down to earth, making quantum electrodynamics a tool that any grad student could use. The impact was immediate. When Robert Oppenheimer, the director at Princeton, and the man who had been most skeptical of Feynman, finally read Dyson's work and a follow-up note from Feynman, he relented. He famously sent a short note to Feynman that simply read, "Nolo contendere," I do not wish to contend. The battle was over. The squiggles had won, not because they were prettier, but because they were the most powerful language humans had ever devised for talking to the microscopic world. Dyson didn't just find a bridge. He built the road that every particle physicist has walked on for the last 75 years. He transformed Feynman from a misunderstood eccentric into the architect of modern physics, proving that sometimes, to see the deepest truths of the universe, you don't need more equations. You just need a better way to look at the picture.